Friction. Before working on this video, you need to know how to apply Newton's laws of motion. If necessary, you should refer to the following video, which covers this topic. Thanks for watching this video, and don't forget to like, subscribe to the channel and activate the notifications. It's very important to the continuity of this channel. Whenever the surface of one body slides over another or tries to slide, there are invisible imperfections on the surface, which causes difficulty in movement. This sliding resistance that is always opposed to the relative movement between the surface is called the frictional force. Suppose a block is sliding on a horizontal surface. As expected, the block slows down and then stops. This means that the block must have an acceleration parallel to the block's surface, in the opposite direction its velocity. From Newton's second law, then, a force must act on the block parallel to the surface, in the direction opposed to its velocity. This force is a frictional force. In the following figure, the block is at rest and there is no attempt at sliding. It is in equilibrium under the action of its weight and the upward normal force, which is equal in magnitude to the weight and exerted on the block by the floor. There is no force acting in the horizontal direction. Thus, there is no friction force to stop the block. Friction also arises whenever there is a tendency for motion, not necessarily motion itself. If you try to slide a box across the floor, the box may not move at all if you don't push hard enough, because the floor exerts an equal and opposite friction force on the box. This force is called the static friction force. Static friction. Frictional force caused by an applied force on an object at rest before motion. In the figure, the man pushes the block and gradually increases the force F on the block. At first, the block remains at rest because as F increases, the force of static friction also increases, staying equal in magnitude to F. Stronger applied force, the block remains at rest yet. Until at this moment, force F attempts sliding but is balanced by the frictional force. Thus, box remains at rest. Stronger applied force, the block just about to slide. At some point, however, F becomes greater than the maximum friction force that the surface can exert. The block then breaks loose and starts to slide. When sliding is just about to occur, friction is said to be maximum. The maximum static friction force is given by the formula Fs frictional force and normal force. Mi sub s coefficient of static friction. The frictional force drops abruptly and stays at that constant value as the object accelerates. Once moving, the frictional force that then opposes the motion is called the kinetic frictional force. Kinetic friction. Frictional force when an object is in motion. The kinetic friction force is given by the formula F sub k frictional force and normal force, mi sub k coefficient of kinetic friction, no unit. We use the same equation to find the magnitude of frictional forces, but with the right situational value, and mi sub k almost always less than mi sub s. The figure shows how the friction force varies. if we start with no applied force and gradually increase the force until the object starts to slide, when F exceeds the critical value and the block begins to move. This is a well-known phenomenon of everyday life. It takes a lot of force to get a heavy piece of furniture to start moving. You must exceed the maximum value of the static friction force. But once you get it moving, pushing it along becomes easier. A 20 kilograms crate is at rest on a floor. The coefficient of static friction between the crate and the floor is 0.7, and the coefficient of kinetic friction is 0.6. A horizontal force F is applied to the crate. Find the force of friction if F equals 20 newtons, F equals 100 newtons, F equals 180 newtons. First of all, we must find the maximum force of static friction and the magnitude of the kinetic frictional force. The maximum frictional force that can develop between the crate and the surface is 137.2 newtons, and the kinetic frictional force will be equal to 117.6 newtons. We see that the motion will take place when the pulling force is just barely larger than 137.2 newtons. We apply Newton's second law in the horizontal and vertical directions, including the friction force in opposition to the direction of motion of the crate. We apply Newton's second law in the horizontal and vertical directions. The component of the resultant force in the vertical direction is 0, so the weight is equal to the normal force. In item A, the force F is equal to 20 newtons. As long as the force F is less than 137.2 newtons, the force of static friction will keep the crate stationary. Newton's second law tells us that the friction force is equal to 20 newtons. In item B, the force is equal to 100 newtons. And we know that the crate will not move as long as the force F is less than 137.2 newtons. Newton's second law tells us that the frictional force is equal to 100 newtons. In item C, if the force F equals 180 newtons, the applied force is greater than the maximum force of static friction. So the crate can no longer remain at rest. Once the crate is in motion, kinetic friction acts. Then the frictional force is equal to 117.6 newtons. A brick of weight 40 newtons rests on a horizontal surface. The coefficient of static friction between the brick and the surface is 0.6, and the coefficient of dynamic friction is 0.25. A horizontal force F is applied to the brick, its magnitude increasing uniformly from 0. Once the brick starts moving, the pulling force no longer increases. Estimate the net force on the moving brick. The component of the resultant force in the vertical direction is 0, so the weight is equal to the normal force in magnitude. Let's calculate the maximum frictional force that can develop between the brick and the surface, because as long as the horizontal force F is less than the maximum frictional force, the brick will remain at rest. So motion takes place when the pulling force is just barely larger than 24 newtons. Let's find the kinetic frictional force as well. Once motion starts, the frictional force is equal to the kinetic friction, and the horizontal force has 24 newtons of the magnitude. Applying Newton's second law in x direction, we get the resultant force. The resultant force is 14 newtons. A block of mass 2.5 kilograms is held on a rough inclined plane as shown in figure. When released, the block stays in place. The angle of the incline is slowly increased, and when the angle becomes slightly larger than 38 degrees, the block begins to slip down the plane. Calculate the coefficient of stereo friction between the block and the inclined plane. The forces on the block just before slipping are shown in the free body diagram for the block. Remember to rotate the coordinate axis to align with the incline. Weight is straight down. The normal force pushes perpendicular to the incline. Friction acts parallel to the incline. Because the block is about to slip, the frictional force is the maximum possible static frictional force. Write the parallel and perpendicular components of weight. The perpendicular component of the weight is directed opposite the normal force. The parallel component of the weight is directed opposite the frictional force. Equilibrium demands that the normal force is equal to the component of the weight perpendicular to the slope, and the friction force is equal to the parallel component of the weight. We can now combine the equations to get the coefficient of static friction.